All right, good morning, everybody. We are the Air Quality Group. My name is Vincent.
Stacy.
Bob. Alan.
Johnny.
Sharon.
Hi, and this past week we want to show you some of the results we came to when studying PM 2.5 emission sources. So, first question is, what is PM 2.5? So, particulate matter that is less than 2.5 micrometers in diameter fills the air, and it's actually been linked with negative human effects, such as cardiopulmonary disease, lung cancer, lung disease, and so on. And so, in order for state governments, local governments, and even federal governments to be able to assess their constituencies and the human health factor of their local regions, it's important to know what kind of PM 2.5 levels are around the area and kind of assess the air quality of the region. So right now, actually in the United States, they have these PM 2.5 monitoring stations. However, they are sparsely located primarily along the eastern and western coasts. And so one of the things about these monitoring stations is that obviously we can't be able to assess a lot of the Midwestern regions as well as the kind of the Rocky Mountains sort of area. So at the current moment, there is actually a model already developed by the United States EPA. It's called CMAQ, the Community Multiscale Air Quality Model. And essentially what CMAQ does is estimate what PM 2.5 levels are at the monitoring stations. However, we see that CMAQ has a lot of inaccuracies, and you see that darker shades of red actually indicate more inaccurate measures. And you kind of see that this is sort of geographically oriented, where in the higher elevation areas, such as the Rocky Mountain ranges, there's greater inaccuracies from CMAQ. So one of the things that we wanted to do as a group is try to do kind of like a 1-2 punch. One is to better CMAQ, at least at measuring PM 2.5 levels at the monitoring station locations, but also be able to try to form a model that can estimate PM 2.5 levels in areas that are not at the monitoring stations. And so to do that, we first started off with hierarchical clustering analysis. This was sort of a way to kind of see, is the inaccurate readings of CMAQ sort of based regionally? And what we found is that is not the case. So if you look here on day 3 of 2011 of the year 2011, we see that the clusters are formed as such. But then if you look over to day 90, some of the clusters are starting to switch. They're not as dramatic right here, but if you flip over another 90 days, you see that some of the clusters that were originally formed on the left side are no longer on the right side. And if we just keep going temporally, you see that there's more and more variation in the types of clusters there are. And so the kind of intent to formulate linear models based on different timescales or different geographical regions over the course of a year would not hold. So instead, our group has decided to go for a more generalized United States map sort of way, as opposed to trying to focus on Midwestern, Pacific Northwest, etc. regions.
Okay, so we had a data set which had 31 variables in it. So the first thing we obviously had to do was start with the basics. So that's what we did. That's our linear regression model. That's the first thing we do as statisticians, right? So we fitted our linear regression model here, and we started off with all our covariates versus the response variable being PM 2.5, and then we did the residuals of PM 2.5 with all the covariates. So the idea was to extract just the adjusted R-square out of the entire output of F statistics, p-value, MSC from the summary. And these are some of the values of the adjusted R-squares that we got. And we also made the residual plots, as we can see here. So the plan was to compare these R-squared values with these correlation plots that we generated, and we kept our threshold for decision at 0.8 here. So what we were able to do was the ones highlighted in yellow were the ones which were highly correlated, and so we can take them out, and when we compared their R-squared values, they were also lower. So that made sense. So we could take these covariates out from our 31 variables at this point. Also, there were some observations which were repetition, meaning they were taken at the same station, but like by different agencies maybe. So those were also out. So at this point, we were left with 25. And then our next step was to see if we needed any transformations going forward, right? So transformation, for that we did the plots. This is just one of the outputs here, which shows, as we can see, there is a pattern. And most of our outputs, which we observed, showed either like a negative or like a slightly positive, highly positive. So there was some pattern that we observed, which was good. And it was also the linearity, like most of the covariates followed that linearity. So it was, which made our life so much easier because we didn't have to go through all the transformation process, and we could just stick with the linear models. And going forward, that is what we did, and we went ahead. And so we were able now to, and yeah, we also observed some covariates which had just like oscillating values for 0 and 1 over here, or maybe just like blobs, meaning all the observations were just concentrated at one point. So those were also out. So based on all these analyses, eventually we were reduced from 31 to 15 covariates at the end, and no transformations, so just linear models.
All right, so now let's dip into some fun math part into one of our models, random forest. This is a very classic model. Everyone knows about machine learning. So, but what is it exactly? So, forest, must be consist of trees. So let's start with a tree. All right. The tree over here is a decision tree where you want to split your data by different categories, consist of different values of different covariates. So you can consist a set of maybe elevation is like larger than 100, while our temperature is less than 70 degrees. And then you make a split here and split the data into half. And then you make such similar splits until you reach the end node where you have the value of all the data points inside that certain split. And you take those values as your prediction value. For your tree 1. So this is how you get the prediction for one tree. And for random forest, you want a bunch of trees because you want to improve decision. So you bootstrap all the data, so you get like tree 2, tree 3. And for our model, we got 500 trees, which took us like around 2 hours to run the whole thing. And we got two forests. I mean, I can mention that in the next slide. And then when every tree you get a prediction value, and then you just average out the prediction value. That will be the prediction for the random forest model as a whole. And the algorithm chose to have 5 variables to do the split every time. And the mean square error is like 0.1. It's like logged scale of PM2.5. So a normal value of PM2.5 is usually around 20 or 50. So even it's logged and the 0.1, MSE is still very low for our model, and it covers like more than 70% of the variance, so which is good. Next, now pass on to the next model.
So here are some other fun math behind the spatial model. Here we have the equation for our spatial model. This part is actually just linear model we use, and this part is our covariance, the covariance matrix that we incorporated into our model, and here's the delta. So let's look at the covariance matrix, which is what makes this spatial model very special. We use exponential function as the entry of covariance model. Here the rho is a scaling parameter, distance between two locations where x1 and x2 are different locations, and here is the range of distance. Let's look at this plot here, this graph. It resembles the real world case where the distance between, the correlation between two locations actually goes down with increasing distance between two locations. That's why we choose this exponential function. And we have this covariance matrix here, where this one will incorporate into our conditional normality equation. This equation is what we use for prediction. We use this V is our new data point and U is our training data set. We make prediction on our new data set based on the training data. And we have an equation here where we have E of V, which is the expected value of new data point, which comes from our single linear regression model that we mentioned before. And here is the covariance matrix of these of our new training data set and our new data set. Then we'll have more introduction about this.
So following some of the computation behind the spatial model is what we have next, Kriging. And for those of you who don't know, Kriging is an optimization to our problem that sort of generates an estimated surface among a given scattered set of points, which in this case is our monitoring stations. And each of those points have their own z-values, which is our PM. So, and Kriging follows this idea of a weighted proximity. So, if, for example, if you have 2 points A and B, and the third point C, for example, that's closer to A than B, that means that the PM, estimated PM of C, should be closer to A than it should be to B. And since we used the linear model, so we didn't have to do any transformations. These are the betas are the weights of the covariates, which are the x's. And one interesting complication that we had while creating, while undergoing the Kriging process for each of the days 1 to 365 was that some of the days, since we had to invert the matrix, as Cece said before, some of the very, very small entries inside the matrix actually were seen as 0 in implementation. So that kind of negated the linearly independency of the matrices, so we couldn't invert them. And therefore, unfortunately, we had to remove a few of the days out of our training data. And we were provided CMAQ models for January 1st and August 1st. And here is the January 1st measurements of the monitoring stations with their respective PMs taken on a natural log scale. And so these are the prediction maps that we made for our 3 models. CMAQ was provided to us. Let's use this. Right. All right. CMAQ is provided to us. Simple linear regression is what we used initially, and then we used more complicated models such as random forest and spatial analysis using Kriging. And some of the notable differences that you can see here is that this declining patch of blue in the sort of western region, and also I think Seth mentioned this earlier, why the Portland and Oregon area is so like red. This is because there are so few monitoring stations in the northwest that it kind of generalizes over that area. So for now, we don't know which of these maps is actually accurate. This is just like a preliminary introduction to these models, and we'll sort of explain, sort of analyze them later after we figure out which of these are more accurate than the others. And these are the August 1st measurements, so it's more concentrated towards the east side, the other levels. And spatial analysis, there's actually better smoothing, you can see. All right, okay. So as the questions that Alan brought up, like we have so many predictions, but they look like a little bit different, but we don't know which one is better. So how do we know which one is better? So we did 5-fold cross-validation, which is that we divide our data into 5 folds, and each fold consists of 1/5 of the whole data points. We use the first 4 folds to train our models, and then we use the 5th fold to test our models. So we are trying to make a prediction on the 5th fold and see if our prediction matches the result in the 5th fold. So we use the 2 metrics as our measurement. One is MSE, mean squared error, and another is MAD, median absolute deviation, to see which model has a better result. So we have some interesting results. Here you go. So first line shows the MSE and MAD for the CMAQ model, which is given. It has an MSE of 51, which is pretty high. And then we incorporated our CMAQ and other 30 covariates into our simple linear regression model, and it tremendously drops the MSE to 23. So we can say that our simple linear regression model is like double better than the CMAQ. But even more than that, our random forest, after we trained the forest for 2 hours, okay, something got to pay off, right? So it dropped the MSE even more to 13. And once we incorporate spatial analysis, I think it took us another 2 hours to run the spatial analysis model, but we were really happy to see the results of this not like 9 of MSE. And the MAD just as another measurement and just corresponding to the order we got from MSE. So theoretically, we can say that spatial analysis is the best, random forest is second best, single linear regression is the third best, and they all beat CMAQ. And we can validate this point by looking back into the predictions map we had before. Yeah. So here you can see that this is a measurement. This is the actual values from the stations. And here's a prediction for CMAQ. As you can see here, CMAQ does a pretty decent job for the eastern half of the US, because eastern half of the US has so many stations. But for the western part, there are very few stations. So as a result, CMAQ predicts the west coast it's super extreme, super dark blue. But once we had a better MSE regression model, you can see the west coast color. We're using all the color in the same scale. So the west coast color leans more towards most of the station measurements here, light blue. And you can also notice that in the actual measurement stations, around Utah state, there are some yellow and orange. But before CMAQ, I barely had any yellow and orange around this area in general, but CMAQ improved it to be smoother. And this pattern can be also seen in the random forest model. Here, the west coast color is even more towards the actual color, and it transitions to more a larger area of orange and yellow here. It just everything is smooth. And for our Q model spatial analysis, you can see it's actually doing a lot better, and it's interpreting here more smoother. Yeah. So we can see the same pattern for another day's measurement on August 1st. The CMAQ, I'll just go through it very quickly. You can compare it to the measurement station map. Here's single linear regression model. Here's random forest. Here's spatial analysis. You can go back and forth and see how it matches. So we can actually visually see some improvements, which is very exciting for us. Yeah.
So our final conclusion is that spatial analysis makes the best predictions. And here are some of the potential improvements we could have made to our projects. So firstly, right now in our current model, we assume that every two covariants are independent of each other, but actually they're not. So maybe looking at the interactions between covariants can improve our models. Also, we might also consider looking at some other machine learning methods like neural network. And also by looking at the residual plot at different seasons, we notice that some areas has different patterns in winter and summer. So in the future, we might also consider building a regression model based on seasons. And also we need to focus more on the Midwest area because our model is most inaccurate in that area. So lastly, we want to thank our postdoc mentor Yawen and our graduate students Amanda and Susan and Dr. Gao for helping us on spatial analysis. And all of us learned a lot here at SAMSI, so thank you all.
Now we're open to questions.
Any questions? Sure. Why did you choose to use 500 trees instead of forest?
Because that's that's a relatively large number to run. We got a good result of MSE, but we started off by 2 trees, and the MSE was already very low, and then we tried 10 trees, and then we decided how much time we want to contribute for the computer to run. And we also got advice from our graduate student Amanda. She did a similar analysis.
I think Yuan already had some results, and 500 was the number. Because I think when we did our first presentation, we only had 2 trees. And I think that's when you asked the question. And after that, we discussed that with you. And she has some previous results, so we needed something to compare our number with. Should we use 1,000 or 100? So that's how we came up with comparing it what we had previously on the data.
Yeah.
So why did you choose to use exponential covariance function to do your other methods?
Yeah,
I think
yeah.
CC explained that, so maybe you could.
Yeah, but it can be more intuitive. Like,
So she has it in the maths slide.
yeah. We can go back to the
Maths
So
slide.
you know, so like how the exponential function looks like, right? So the x-axis is distance, and the y-axis is whatever you want to measure. So we think this function resembles the real-world experience in terms of PM2.5 concentrations dynamics according to distance. So like theoretically, like 25 meters away, for example, the air you breathe is quite different from the person 25 meters away to the air he breathes, and it drops down like very quickly once you goes over that like for example 25 meters threshold. So we think this process resembles the real world issue. Yeah,
And
that's
if we
why.
were to do it, like if we had more times on our hand, as CC was explaining, we would have done the matern, which is what Dr. Doug also, I think when he took his R session, he mentioned that. So, but since we didn't have a lot of time on our hands, so exponential is like a special case of matern, so we went ahead with that.
With the CMAQ model, it seems like the intersection of the map that wasn't shaded in. Do you think that was due to missing data, or is it just like a limitation of the model?
So can I go back to CMAQ?
Which one?
CMAQ, SAMSI, that's what you're referring to?
No, it should be the obvious first.
Okay.
What was the question one more time?
So it seems like part of the map isn't shaded in. Is that due to missing values, or is it a limitation of the model?
It is missing values.
These are missing values,
Yeah.
the ones that you don't.
No, so
This
I think
station.
it's just because how you set the range.
Yeah.
So there should be no missing value there.
This is just an extrapolation from the stations that we had, but this other side, there was a map which showed the stations, and it was just extrapolating whatever the stations had. So there is no missing values. So I think it's just, they just
Just the range.
enlarged.
Yeah, because we also have white over here, somewhere. Yeah.
Alrighty, let's thank them again. And